Hey folks, Mrs. White here. Some exciting news. Section 12.3 is on the docket for today, and it is the last new learning we have for statistics for the year. And I know that seems kind of crazy because we still have like 3 weeks left of school. What the rest of the time together is going to look like is a review for a Chapter 12 test, the Chapter 12 test, and then you're going to have about 2 weeks to work on and finish a little project that's going to summarize your learning for chapters 10, 11, and 12. And that's going to be open note, open book, open resources online. So that will be for you folks to work on independently. And I'll be giving you all the support materials for that as we get closer. So for now, let's just focus on our last new thing, which is super duper exciting. And then we'll review all of the ways that we can test for difference in chapter 12 when we get together next time. So today we're going to be focusing on two dependent proportions. Now, whenever we're doing two of something, that's generally what we did in chapter 11, right? We compared two independent proportions. We compared two means that were dependent or independent, and we compared two we compared two standard deviations, okay? So we had a lot of comparing twos in our last chapter. However, in this chapter, we haven't had that a lot. We've been dealing with contingency tables, right? Where we're maybe comparing two variables, but if we're comparing different samples, there's going to be three or more. Well, today we're going to be comparing two samples again, but we're going to be looking at proportions specifically, and they're going to be dependent proportions, which means, and you'll see as we get going, that the two samples are interrelated. So we're going to talk about when and this would come up and why would we use it. And then we're going to do a hypothesis testing. We're actually going to do two examples, not one. Both of them are on that note-taking guide if you decided that you wanted to download that and use it. So the first example we're going to start talking about, we're going to circle around to and do that as our second example at the end. You do have only two homework problems. I would encourage you folks, please, look, there's only two, okay? Give it a go. Make sure you submit it, all right? So let's take a look at our sit and begin first. It's important for us to review how to determine if things are independent or dependent. So we're going to talk about that first. So which sampling, based on these three problems, what is the sampling? Is it independent or dependent? And then the response variable, which remember is the data that you're collecting, is it qualitative or quantitative? And so we'll kind of take a look at that also. This is from chapter 11 or section 11.1, where we first started talking about independent and dependent sampling strategies. So let's take a look at number 4. A researcher wishes to determine the effects of alcohol on people's reaction time to a stimulus. She randomly divides 100 people aged 21 or older into two groups. Group 1 is asked to drink 3 ounces, and group 2 drinks a placebo. Both drinks taste exactly the same, so the individuals in the study do not know which group they belong to. 30 minutes after consuming the drink, the subjects of each group perform a series of tests meant to measure reaction time. So we see there's two groups. Does the second group depend on the makeup of the first group? That's how we would determine independent or dependent. And the answer is no. They're two separate groups. People were randomly selected to put in each of those groups. So this would be an example of an independent sampling strategy, okay? Then we're going to look at the outcome. So what they're doing is they're measuring reaction time. They're measuring the amount of time. That means that we're dealing with an amount of something. We're dealing with a quantity, so it's quantitative. Okay. Next problem. A political scientist wants to know how a random sample of 18 to 25-year-olds feel about Democrats and Republicans in Congress. She obtains a sample of 1,030 registered voters 18 to 25 years old and asks, do you have a favorable or unfavorable opinion of the Democratic or Republican Party? Each individual was asked to disclose his or her opinion about each party. So, right here, we're taking a look. Okay, she's doing a random sample. Does it matter? Let's see. She obtains a random sample registered. She asks, do you have a favorable or unfavorable opinion about the Democratic Republican Party? So what she does is she asks the first question, do you have a favorable opinion about the Democratic? Then she asks, do you have an unfavorable opinion of the Republican Party? So really, she's asking the same people a question twice. Okay, she's trying to, since the sample is going to be the first question and then the second question, this would actually be considered a dependent problem. because the same person is answering the first question and the second question. So she's looking to see about the relationship between the two. Okay. Then she's asking an opinion, so whether it's favorable or unfavorable, and that is clearly non-numerical, right? It's a category, so this would be qualitative. They're measuring some sort of quality, if the people think they're favorable or unfavorable as far as Democratic and Republican. Let's take a look at our last one here. A psychologist wants to know whether subjects respond faster to a go or no-go stimulus or a choice stimulus. With the go, no-go stimulus, students must respond to a particular stimulus by pressing a button and disregard another stimuli. In the choice stimulus, the subjects respond differently depending on the stimulus. A psychologist randomly selects 20 subjects, and each subject is presented with a series of go, no-go stimuli and the choice stimuli. So it's the same people in both groups. This means that it is dependent, just like the one above, right? It's the same people that are being asked the same questions or different questions above. So the same people are going to be in both of those groups, okay? Then the mean reaction time. So the average is what we're looking at here, but it would be reaction time. So it's the amount of time. So that would mean that it is quantitative because we're measuring how much time. Dependent, quantitative. Dependent isn't always with qualitative or quantitative, okay? It can go either way. Similarly with independent, right? Okay, independent can happen quantitative or qualitative. So now that we've kind of touched on that a little bit more, let's take a look specifically at two population proportions. So remember, proportions are your fractions or decimals, okay? Your piece over your whole, within dependent samples. So again, in chapter 11, we looked at two proportions for independent samples. In fact, when we had to check two things, one of the two things was that it was independent. So at that point, we hadn't done anything really with dependency. So now we are. Okay, so what's going to happen is you're going to be given a situation like this. So we're comparing two different ointments, okay, that are supposed to help with poison ivy. So let's say you could have two totally different samples, and you could give one sample group ointment A, and you could give one sample group ointment B. With two totally separate samples, that would be independent. But we're looking at dependent now. So maybe what happens is you have a sample of people that have poison ivy on both arms. So they have it on their left, they have it on their right, and on one arm they put ointment A, and on the other arm they put ointment B. So if you think about this, right, the way that a person reacts, because it's on the same person here and here, they're both in the first sample and the second sample, right, that would take care of potentially a lurking variable. So if ointment A worked but ointment B didn't work, then we could say you don't have to worry about whether that person just reacted differently. They're the same exact person. So that's kind of the idea of this, okay? In this dependent sample, they're the same people, so it takes care of a lurking variable potentially. So here, what we would want to do, because we're dealing with proportions, is we maybe could at first, if you were trying to figure out which of these worked better, you might do like the proportion of ointment A. Okay, so let's do P hat of A and P hat of B. So if we're trying to measure like the success of ointment A, we would look at all the people that were healed, right? It would be your 293 would be our piece plus our 31. This is the total amount of people that were healed from ointment A. Whether ointment B worked or not, who cares? This is how many people were healed. And then we put it over our total amount of people, which we'll figure out in a second. If we were looking at ointment B and we want to figure out how successful that was, we would add these two items together, right? These are all the people that were healed from ointment B. So it'd be our 293 again, which means that they were healed on both arms, and 43. Now we do have to, because we're dealing with a proportion, deal with piece over whole. So to figure out how many total people were surveyed, we'd have to add all four of these numbers. So I'd have to do 293 plus 31 plus 43 plus 103. And if I added all those up, I'd get 470. It looks like 6, 7, 8, 9, 10, 370. Yeah, 470. So that becomes the denominator on each of those. So if I were to add across the top here, 324 over 470. And then here I would get 336 over 470. And again, if we're comparing proportions, it's easiest if they're decimals. So this one comes out to be 0.689 or approximately 69%. And then if we look down here, 336 divided by 470, well, that's going to give us 0.7149, so kind of like 71.5%. So what this means, okay, because we're dealing with the proportion of A, we could say 69% of all of the people were healed by ointment A, and then we could have 71.5% of people were healed by ointment B. That's what this means. Okay, now we could compare those, but what we really want to do is we want to be able to do an inference, which means that we'd be doing some sort of hypothesis testing to determine if that is statistically significantly different or not. Okay, they seem pretty darn similar. Are they close enough based on how many people were in this whole study? If there was more people or less people, that would change it, right? Our N value is important here. So every time, and I mean it, every time that we're doing an inference about two proportions that are dependent samples, our null hypothesis is always going to be that our proportions are equal, right? That there's no change. So the proportion of sample A is going to equal the proportion of sample B. And here I'm using A and B because those are our ointment names. Our alternative is going to be that they're not the same, that they're different. We're not going to have greater than, we're not going to have less than, we're going to just have that they're different. It is always going to be, oops, this should have been a P, I apologize, proportion of B. That they are going to be the same for our null and then just not equal to or different for our alternative. Now from here, we would have to do, some more steps to do our normal hypothesis testing, and we're going to have its own test statistic. And some bad news is that this is actually dissimilar to most of the tests we've done in the past. We are not going to go into the stats test menu here. You actually have to do a handful of things by hand, whether you do p-value or traditional or classical method, excuse me. So let's take a look at both. To do a dependent or hypothesis test of two proportions, you are going to have a contingency table that looks like this. Okay, so there's going to be two separate treatments happening to the same group. Okay, that's how it has to work. They have to be happening to the exact same group. And then you're going to have a column for success, a column for failure, a row for success, and a row for failure. And they use these denotations right now just to kind of give you some guidance, because we're going to have to do some additional calculations below. Okay, and these are things that have to be done by hand. Okay, so when you identify that you're doing two treatments to the same group, which means that it is a dependent proportion situation and you have a contingency table set up like this, before you do anything else, you're going to make sure of these two things, which is a little different, right? Before, we were writing our null and our alternative and doing these items after we found our expected values, but now we're going back to the way we used to. We're going to check these two items first. So first things first, are they dependent and are they obtained randomly? So normally we would check independent and random, right? Well, here we need to double check that they are dependent and random, which makes sense. Then, this is a little bit different also, you need to take your total of observations where the outcomes differ, okay, and you have to add them up and see if their sum is greater than or equal to 10. So what that means when the outcomes differ, it means if this is happening to the same person, a difference would be where they have a success on one and a failure on the other. So this number represents a success here, but a failure here. And this number represents a success here, but a failure here. So if you think about it, these are errors, right? This is like, you'd assume if both treatments were good, they would both be the same. That's our null, right? So these are actually where your errors would occur. Is going to be where a success and a failure happens. So we're going to add those two items up every time, and we have to make sure that that is greater than or equal to 10. Okay, to be able to consider going. There's no test for normality or anything here, but you do need to verify that first. So these are your two assumptions you have to make to be able to do this test. Okay? So as we get going and start following the actual steps to do the hypothesis testing here, I do want to let you know what this is called. I don't mind if you name this test two dependent proportions. That's perfectly fine to write two dependent proportions. But if you were to look it up online or in your textbook, it's actually called McNemar's test. So McNemar's test. This is an E, sorry. McNemar's test. And that's the way that we do, again, a test of two proportions from a dependent sample. All right. So if you were taking that chapter 12 exam and it asks you which test, you can write two dependent proportions, or you can write McNemar's test. So anyways, let's move on with this test. So after you verify that those two things are true, you would keep going. Again, your null is going to be that the two proportions are equal, and your alternative is going to be that the two proportions are different from each other, always, every time when we do McNemar's test. So you will select a level of significance. If they give it to you, great. If not, you want to think about how severe or serious making a type 1 error would be. If it's not that bad, then you could do 5% or 10%. If it's very serious, then you would choose only 1%. Excuse me. Next, you have to compute your test statistic. And it says compute test statistic, and that is serious. You will have to compute this by hand. So I want you to circle it. I want you to write it down. I want you to put a little star next to it. And I know that these numbers are strange, right? These are not the normal numbers that you would see. Usually we have like observed minus expected or vice versa. But here we're dealing with, again, the errors. So you're going to find the difference of your two errors. Here you used the sum, but you'll find the difference and square it. That way, if it's negative, you're taking care of the negative. And you put that over the sum of the two errors. So you do it, and really the subtraction here doesn't matter because when you square it, it's going to make it positive. So you'll subtract the 2, square it over the sum of your two errors. And that's still, it's a chi-squared distribution that we're using in McNemar's test. I'm not going to show you where this comes from. In fact, this little star delineates in your book that they're not even going to go over it because it kind of is harder than what you would need to know for this course. So don't even worry about it. Okay. So we're still using chi-squared of our null. We're looking at the difference of our errors squared over the sum of the errors. So let's actually do one of these now. And I did put the TI-83 information up there for you, so you can reference it if you'd like to. But as you can see, there's no stat test button, okay? You still can do this using the classical method or the p-value method, and we'll go over both. In fact, I think classical here is a little bit easier, personally, just because the keystrokes are different than what we've done since like chapter 6. So let's check out this problem. A recent general social survey asked the following two questions of a random sample of 1,492 adult Americans. Under the hypothetical scenario that the government suspected a terrorist act was about to happen. Okay, so they found 1,400 people. They said, okay, so the government suspects that a terrorist act is going to happen. And then they ask the same people these two questions. So again, same sample, two separate questions, okay? Do you believe the authorities should have the right to tap people's cell phone or telephone conversations? Do you believe that authorities should have the right to stop and search people on the street at random? And the results are in this table, okay? So you had people who agreed with random stops and agreed with phone taps. You have people who agreed with random stops but did not agree with phone taps, and then the other combinations there. So they're asking you, do the proportion, so this is letting you know you're dealing with a proportion, of people who agree with each scenario differ significantly. Use a 0.05 level of significance. So we see here that it's the same people in both group. They say that these people were selected randomly. So as we're thinking of our two items that are really important to be able to do, they just said that it's the same people, so we know it's dependent. And they said they were selected randomly, so we know it's dependent and random. Okay, that's our first thing we have to check. Next, we have to look at our errors, which would mean that you agree with one but disagree with the other, and agree with one but disagree with the other. And you need to add them together and make sure that that sum is greater than or equal to 10. And clearly that's like 400 and change, right? So that's definitely bigger than 10. No big deal, okay? So we've done this. We've done this. We know that our alpha is going to be 0.05, okay? And now we're ready to write our null and our alternative. So our null is going to be that the two proportions, which means that they agree with both or disagree with both, okay? Our proportion of stopping is going to equal the proportion of people who agree with a phone tap, okay? That they're the exact same. Our alternative is that the amount that people differ, okay? That their opinion of each scenario differs. So we're looking at the proportion of people who think it's okay or agree with stopping to not equal the proportion of people who think it's okay to tap a phone. Okay. So there's our null and there's our alternative. Again, every time it's going to be equal and does not equal. And I like to delineate which of these go with which P. Okay, by using that versus just labeling this A and this B, which you're welcome to do, but then you need to make sure you label it on here so that anyone reading your work could understand that. So here's the dilemma. There's no keystroke to find your test statistic, okay? In the past, I've been like, oh, let's calculate it. And then I'm like, surprise, it's on the test anyways. Here it is not. You can see in the calculator section, it says you have to calculate it by hand, okay? So to find the test statistic, we're actually doing a chi-squared value of our null. And again, that's our test stat. And we're looking again at our errors, right? We're looking at where they don't match up quite right. So on the top, we're going to do the difference between these two. So we're going to do our 335 minus our 126, and we're going to square it. That way, if we subtracted them oppositely, or oppositely? Whatever. If we subtracted them the other way around, and it was negative, the square would help cancel out that negative. And then we're going to put it over the sum of these two items. So our 335 plus 126. This is not a hard calculation. It's just kind of annoying. Okay. So if we take these two and we subtract them, so we would have 335. Oops, let me clear this out. Sorry about that. Whoa, let's second quit out of that. Now we'll clear. Okay. So we have 335. What was it? 335 minus 126. So that's our difference, our numerator. We have 209, and then we're going to square that 209. So we're going to take it and we're going to square it. We end up with 43,681. So let's just take a second. We'll write that in. 43,681 over, and then we need to do the sum of these. So let's just take a second and add that up. It'd be 450 and 11, so 461. So I'm going to take a second. I'm going to do this divided by 461. So this number divided by 461. Oops. And I end up with 94.75. 94.75. Now, at this point, now that we have our test statistic, if you're comfortable with the classical method, I actually would encourage you to do the classical method here because I think that it's easier because you do the exact same thing you would normally do. Okay, so normally in classical method, we do a little sketch because we're dealing with chi-squared. We're going to be using the chi-squared distribution. So we're going to have to find out the chi-squared value for 0.05 here. And then we're going to see, is this 94.75 going to be in this part, the non-shaded area or the shaded? If it falls in the shaded area, then there is enough, right? If it's in the shaded area, we say, yes, there's enough evidence. If it's not, then we say, no, there's not enough evidence to reject the no. Okay, so to find the chi-squared value, of 0.05, I'm going to go to the insert of my book, which I actually have open. I thought I had open right here. And here's the clincher that you need to make sure you write down in your book, okay? When you are finding your chi-squared value for classical, you always treat degrees of freedom as 1. Okay, it doesn't matter that we asked 461 people. We are not going to use that as our degrees of freedom. You are always going to use a degree of freedom of 1. Okay, so we're going to go to table 8, degree of freedom 1, and we're going to go over to 0.05, which is right here, and I see it is 3.814. So I'm going to go back now to my presentation. This value is 3.814. Okay, remember, you do degrees of freedom equaling 1, and this is table 5, 6, 7, 8, okay, in the back of your book. So clearly 94 is going to be way the frig over here, right? It's going to be way in the shaded region. So yes, it would be in the shaded region. Yes, there's enough evidence to reject our null and accept our alternative. So there's enough evidence to say that they are statistically different, okay? If we were doing our p-value, and this, like I said, I actually feel like is a little more work. I don't care if you do both, like always on your assessment, you'll get bonus points. If you only do one or the other, that's fine with me. One thing we haven't talked a lot about is that the p-value is actually the area under the chi-square distribution to the right of the test statistic. So if we actually found the chi-squared of 94.75, not 0.05, but chi-squared of 94.75, the area underneath is your p-value. And we've really just used the p-value and just compared it over and over again. We haven't done a lot of that graphing piece. So I'm still not going to make you do the graphing piece. But what it means is if we're calculating area of a curve, and it's going to be from a random amount, then we're going to have to go into our distribution menu, which it's been a while since we did this, okay? So we're going to go into our graphing calculator. We're going to press second vars, which brings us into our distribution menu. And we're going to go down to option 8, which is our chi-squared CDF. And CDF means that you're shading, it's continuous. If it was PDF, it would mean that you have a single probability. We're not doing a single probability. We're doing everything shaded to the right. So we're going to do chi-squared CDF, which is select 8. Or just going down to option 8. After that, we're going to enter our lower bound, which is going to be your test statistic, right? If it's shaded to the right, your lowest part is going to be your test statistic. The upper bound is going to be that there is no bound, essentially. So we're going to do 1E99. And then we're going to plug in 1 for our degrees of freedom again. So that's really important that you remember, because otherwise you'll forget, okay? And you won't be able to do this calculation, whether it's classical or the p-value. That degrees of freedom equaling 1 is imperative. So then we're going to just press enter, and that's going to give us our p-value. So we'll come back down to our graphing calculator. And let's just take a quick look before we get going too much. Our test statistic was 94.75, so I don't want to forget that. So because I'm finding area under a curve, I don't know the area, I'm going to go into my distribution menu, which is right here. So I'm going to go second vars, and that brings me to distribution. And I'm going to go down to chi-squared, but again, I want a whole shaded region, so I'm going to go CDF. So I'm going to go all the way down to 8. I'm going to press enter. My lower is always your test statistic, and our test statistic here was 94.7527. Our upper is that there is no upper, and remember, it doesn't actually hit the x-axis, so we're going to go out to 1, and then we're going to go second, and then comma to get the E, and then 99. And then our degrees of freedom, which is what we always use when we're dealing with two dependent proportions, is always, always, always 1. Okay, always 1. And then we paste it in. So you can see here, if you didn't have the same calculator as me, you would do 3 things separated by commas. You do your test statistic, comma, 1E99, comma, 1. So again, if your graphing calculator is a little bit older than this program, then you're going to need to type those 3 items in on your own, and then press enter. So the area under the curve is not 2.15. I want to remind you, the area under any of these curves is going to be exactly 1. So it could never be higher than 1, folks, okay? And if it's an area that's shaded and there's another area that's not shaded, then clearly it's going to be less than 1, okay, but greater than 0. I want to point out, you need to look at this whole thing. This says E negative 22, which means I moved this decimal point forward 22 places, meaning there would be 21 zeros in front of this too. So this is really, 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 really freaking close to 0, okay? So I would approximate this value to be actually 0. Okay, so that's what I'm going to actually write in here. I could put that my p-value is 2 point whatever with an E negative 22. That's true. But I could also say that approximately is just 0. Okay, and we're going to compare it to our level of significance, which is 0.05. So is 0 less than 0.05? Heck yeah, it is. It's a lot less, okay? So yes, there would be enough evidence. So as far as wording your conclusion appropriately, you would say something like, and I'm not going to write it all out because this tablet doesn't work great, so just listen carefully. You would say something like, there is enough evidence at a 0.05 level of significance to say that there's a difference. Remember, that's what we're testing, difference. So there is enough evidence at a 0.05 level of significance to say that there is a difference between the proportion of adults who are okay with being stopped and the proportion of adults who are okay with phones being tapped. Okay, so that's what you would have to say. You want to say if there's no difference or if there is a difference. Okay, and then again mentioning the level of significance. So this is the only example your book worked through, but I thought it would be beneficial to do another one. So I thought we'd go back to our poison ivy example from the beginning. This one's not in the book for you to check. So if you feel good right now, you can go right to your homework. If you want to go back to this first example, then that's fine with me too. But we're actually going to go through and hypothesis test this right now. So when we would read this problem, we would say, okay, the same person is getting the ointment on one arm and then the other arm. So it's clearly dependent because it's the same person. Okay. So as I'm thinking of my one, it was dependent. And although there was no word problem that went with this, let's say that it was random. Okay. People that had severe poison ivy cases were chosen at random, and ointment A was put on one arm and ointment B was put on the other. So random, dependent, perfect. Our second piece is we have to make sure our errors are greater than 10. So we'd be looking at 43, right? Here's one of our errors. Here's our other errors. We would add them together. Is that greater than or equal to 10? And the answer is heck yeah, it is. Okay? If those two things work, we're ready to move on to our null and alternative. Now, they do not give us an alpha value for this, but I mean, poison ivy ointment working isn't like life or death. But it is like an inconvenience, right? If you have poison ivy and you definitely, if it's severe, you definitely need medication for it. So we would use 0.05, I believe, as a level of significance. And that's what we'll choose it. No big deal. So now we'll do our null and we'll do our alternative. And we already kind of talked about these in the beginning. Our null is going to be that they're equal always, but I would do the proportion of ointment A working and the proportion of ointment B working being the exact same, which means that both medicines work the same. We're testing to see if they don't work the same, okay? Not if one is increased over the other, but that they're just not equivalent. Okay, so we're testing for a difference. So do they work the same or are they different? So I have all of those written now. I have to by hand calculate my test statistic, which is chi-squared of my null. I'm going to look at my difference of these two. So even if I did 31 minus 43, okay, when I square it, it's going to make it positive. So it doesn't really, just want to show you it really doesn't matter which one I do. 31 minus 43 would be 9, 10, 11, 12, negative 12. Negative 12 squared is 144. If we'd subtracted it the other way, we'd gotten positive 12. Positive 12 squared would be 144. And then the sum of those two items is, let's see, 74. Now, if I divide those two, gosh, it's pretty darn close to 2, isn't it? 1.9459. Remember, that's a 9. So this is my test statistic. Now I'm ready to do both classical and p-value. Again, I don't care which one you do. I think classical is easier just because it's so similar to what we've done in the past. So for classical, because we're dealing with chi-squared, we're going to draw our skew to the right. Okay, there's our distribution. We're going to find the chi-squared value for 0.05. And we're going to use 1 degree of freedom. We always use 1 degree of freedom when we're dealing with dependent random sampling. So degrees of freedom being 1, I could go back to that table, I could look at it again, but honestly, it's still 0.05, so it's going to be the exact same. It's going to be 3.814. Okay, so is 1.9 bigger than 3.8, or is it smaller? Well, clearly this 1.9 is going to be over here, right? It's not in the shaded area, so there's not enough evidence to reject the null. Okay, there's not enough evidence. If I were to do this using the p-value method, okay, so I'm going to use 1.95 just on my calculator because it doesn't really make a huge difference, right, when I'm dealing with comparing it to 0.05. So I'll do 1.95. So I'm going to go into my distribution. So second vars. I'm going to go down to option 8, which means that I'm shading my chi-squared. I'm going to press enter. My lower bound, I said I was going to just go out 2 decimal places. It's going to be 1.95. Remember, you always use your test statistic here. The upper is always going to be kind of the infinite situation, right? 1e99 with a degree of freedom of 1. And there you can see if you don't have one where it asks you for upper, lower, and degrees of freedom, that's the order you would put them in, separated by commas. Press enter again, and I get 0.16. So I'm going to compare that 0.16 to 0.05. And is it less than 0.05? And clearly it is not. Okay? It is not. So these two answers jive, which is good. We did the same test twice. The way we would interpret this, okay, or come to a conclusion is we would say there is not enough evidence at a 0.05 level of significance to say that the two ointments work differently. Okay, we're not saying that they are the same, right? We're just saying that there's not enough evidence to say that they're different. Okay. Hopefully that was enough to get you going on these. One big idea is that you'll know you're doing this strategy when you have a contingency table set up like this, right? It's dependent, and then you always have a success versus a failure and a success versus a failure on both axes, right? You have it as your vertical and you have it as your horizontal variable pieces, okay? So give a go to your homework problems. As always, I'll be available during office hours to offer you support. I'm happy to do those 2 problems with you if you so desire, because after this, we're going to be reviewing for our test and taking our last exam of the year, okay? Not the last assessment, right? Because you're going to have that little project, but it is the last exam for the year. So let's make it awesome. Okay, folks? I will talk to you later. Bye.